Okay, so we are going to finish up section 4.9 here. This is going to be the last bit. We got integrals involving e to the x. So we would say if we have the integral of e to the x dx, that will equal e to the x plus c. So the indefinite integral of e to the x. Remember, e to the x is its own derivative, so kind of makes sense if you take the derivative of e to the x, it becomes e to the x, and then the plus c is because the derivative of any constant will go to 0. We also get a corresponding, if you have e to the k, kx plus b dx, that will equal, so it's e to the kx plus b. If you took the derivative, you'd get e to the kx plus b left alone, then you'd have to multiply it by the derivative of kx plus b, which would be k. So what we're going to need is a 1 over k out front to balance out and cancel out the k that would get brought down from the chain rule. Then we have to put plus a constant after it. So we'll take a look at two integrals here. So for this example, it's example 5. We got part A. They want us to figure out what is the integral of 3 e to the x minus 4 dx. And then part B over here, they want us to say what's the integral of 12 e to the 7 minus 3x dx. So for part A, we can go through and we can use that the integral is linear, so that we can say 3 is out front. We get the integral of e to the x dx minus the integral of 4 dx. So we get 3 out front. E to the x is its own integral. So when we integrate e to the x, we get e to the x. And then minus, we think, okay, who has derivative 4? Well, 4x, when I take the derivative of 4x, that becomes 4. So the integral of 4 itself would go to 4x, and then we have to put a plus c after it. So that is that first one. The second one over here, we would put 12 as the constant, so that would go out front. We'd have the integral of e to the 7 minus 3x dx. So the negative 3 is acting as the k, because that's the number that's paired with x, and 7 is acting as the b. So we would get 12, and we could just put the 1 over negative 3. And then the rest of it would be e to the 7 minus 3x. And you can kind of check it with the chain rule. E to the 7 minus 3x, e is its own derivative, leave the 7 minus 3x alone. Then the derivative of 7 minus 3x would be a negative 3. The negative 3 here would cancel with the 1 over negative 3. That would leave the 12 behind, and then you would get the right derivative. We need to put a plus constant after it. And then we're going to kind of combine. You have 12 up top and negative 3 in the bottom. So 12 divided by negative 3 is negative 4. So negative 4 e to the 7 minus 3x plus c. That would be our answer there. Okay, so to wrap up the section, we're going to look at some statements that are called differential equations. So these are equations that involve the derivative statement. So we would say like dy dx equals some expression like, dy dx equals some f of x. Basically what we would be looking for, this right here would say find a function y such that the derivative of y with respect to x is f of x. So basically, it's a statement involving derivatives, and your goal is to find some function y or to find some function that would satisfy the derivative statement. Sometimes you're given initial conditions. Because without initial conditions, a lot of times you end up with stuff like plus c. If you want initial condition, they may say something like, y of 0 equals 5 or something. They'll tell you that this function that you're finding, this function evaluated at some input gives you an output that would be considered an initial condition. And we're looking at initial value problems. Which are basically a differential equation combined with an initial condition. So we're going to take a look at two of these and just kind of talk our way through them and see that they're not too bad. So for this example, we want to figure out, we want to solve dy dx. So we need to come up with some function y that when you take its derivative is 4x to the 7th subject to, and here will be our initial condition, y of 0 equals 4. So basically, what we're trying to do is we're trying to find a function y. So I need function y that when I take the derivative of it, I get 4x to the 7th. So basically, if I think about it, I could set my problem up as y of x equals, so I need the function that when I take its derivative becomes 4x to the 7th. So y of x equals the indefinite integral of 4x to the 7th dx. Because this says basically the integral of 4x to the 7th says that will be the function that when I take its derivative is 4x to the 7th. So this will give me y of x would equal, the 4 will be out here, I'll have an x to the 8th, and I'll need a 1 over 8 out front. And I need a plus constant c. So to get this a little bit nicer, if I have 1 over 8th and 4 up here, 4/8 is a half. So I would end up with 1/2 x to the 8th plus c. Well, at this point, this is where we use the initial condition, y of 0 equals 4. This will let me figure out what the c value is for this particular problem. If you don't have a initial condition, then this is as far as you can really get. But once they tell me, hey, if I have y of 0, that would equal 1/2 times 0 to the 8 plus c. So I'm evaluating y of 0. Y of 0 is supposed to equal 4. 0 to the 8th times a half, that's actually just 0. So I get 4 equals 0 plus c is just c. So I get 4 equals c, and then I can get my final formula. This is an equation that whenever I put y of 0 in, I get 4 back. If I take the derivative, 8 comes down, 8 over 2 is 4, and then I get 4x to the 7th, and the plus 4 disappears. So I have the derivative. The derivative dy dx is 4x to the 7th, and it satisfies the initial condition here. And that is my solution to that initial value problem. So we're going to do one more of these, and then that'll wrap up the section. So we got, this is example 7. We basically got dy dt is sine of pi t, and we want y of 2 to equal 2. So we want to solve this. So my y function, I need to think of who is a function that when I take its derivative gives me sine of pi t. So I need to find what is the indefinite integral of sine of pi t dt. This will be, let's see here, integral of sine is negative cosine. of pi t. When you take the derivative of this, derivative of negative cosine is sine, you would leave the inner part alone. And then the derivative of the inner part would kick out a pi, so I need a 1 over pi out front to cancel the pi that would be kicked out by the chain rule when I took its derivative. And then we'd put a plus c out there as well. So this is about as simple as my function currently can be. So we get that that's our y of x. So now to figure out what's the actual c value that's going to work, we're going to use y of 2 equals 2. So if I have y of 2, that would equal negative 1 over pi cosine of pi times 2, I guess. Would be pi times 2 plus c. Cosine of pi times 2, that's the same as cosine is 2 pi. That right there would be 1. Y of 2 is equal to 2. So we'd have 2 equals negative 1 over pi plus c. Because 1 over pi times 1 is just 1 over pi. So to finish this up, this negative 1 over pi, I would add it across the equals, and I'd get 2 plus 1 over pi is my constant. So then if I rewrite my formula here, I would get y of, sorry, I put of x there, it should be of t. My variable is of t the whole time. So I'm looking for a function y evaluated at t so that my variables match. Okay, so okay, y of t, the function is negative 1 over pi cosine of pi times t, and then it's plus, I'll just write it in parentheses, 2 plus 1 over pi is the particular constant that we want. This is a function when I take its derivative. The derivative of this function is sine of pi t, so dy dx is sine of pi t. And whenever I put 2 in for t, I end up getting 2 back for my variable. And that's going to wrap up section 4.9, so we'll stop there.